Okay, so first, thank you very much to the organizers. I'm also, as the previous speaker, an outsider. Oh, it's okay. Somehow an outsider in the field. I don't work on fast FRBs, but I work on magnetars, so I will try it somehow. I tried in this time preparing the talk to match somehow. We try the connections. What can we learn from the real magnetars we are observing to somehow interpret GRBs? Now, I will somehow divide in three parts. First, let me remind you what a magnetar is. I will start somehow an historical point of view, showing that in the last 10 years, our idea of magnetars changed completely. And then somehow some consideration on connections, possible connections on what we see in these sources with FRBs. Now, 20 years ago, we were, again, with a small sample of sources, a few sources, and we thought they were powered only by magnetic energy because their X-ray luminosity was way too high than their rotational luminosity. This means that there should have been something else. The magnetic field came into place because P and P dot, they were giving very high magnetic fields, that you see here. Many people thought the critical limit on the magnetic field, so the magnetic field at which you have cyclone energy and electrons equal to its rest mass, can be a limit for this. So higher than this, you have magnetary, lower than this, you have radio pulsar. Well, 20 years passed, everything was more or less wrong, or just partial view of the sources. And this is somehow when we have more sources, and those are all the ones that were discovered in the past 15 years, 20 years or so, you realize that, I mean, we had only a very partial view on what those sources were emitting and how we're emitting and what they were actually look like. So they are very variable. They were thought to be stable. Instead, they're extremely variable. They show transient flares. They emit till the hard X-rays. They are actually mostly powered by magnetic energy. I will show you that some of them actually they have a very strong rotational energy too. So just going one by one, somehow the big discoveries that some of them that changed our mind. Radio pulsation were discovered for 4 of them. And so there was no this photon splitting effect that we thought 20 years ago that were somehow quenching their kind of emission. We see radio emission. This radio emission is actually connected with the outburst activity. It's not exactly the same that the radio emission you see in normal radio pulsars. They have some similarities, but also some very peculiar things. I will get to that a bit later. We see rotational powered pulsars showing magnetar emission, flares, and bursts. So things like this source, which is actually a radio pulsar that at a certain point gets an outburst, big X-ray emission, burst, exactly as a normal magnetar. We see magnetars with field of the order of 10 to the 12 Gauss. So actually filling in this part of the plot well below the critical field lines. So this is not a limit anymore. So we have sources where you do the P dot job, and you have 10 to the 12, and they emit exactly as a normal magnetar, nothing different. And we see even outburst, magnetar kind of outbursts from other kind of sources, which are called CCO. I will get to that in a second, for which you see outbursts and X-ray emission from sources that actually were taught because some of them have a PB dot measurement with magnetic field of 10 to the 11. So even if they are very young, they might have got a lot of accretion at birth. So they are very hot, low magnetic field because it might have been somehow get into the crust due to the very high accretion at birth. So they are very weird sources. They also show magnetar activity. So given this, what is exactly a magnetar? Is it a high field PP dot? No, definitely not. We know sources of 10 to the 12. So it's somehow a source for which we detect emission, magnetic emission. So we detect bursts and flare. This source might also have high E dot. They can also be radio pulsars. It's not that one thing excludes the other at all. Okay, just to give you an idea on the different classes that we know now, we know things that are mainly rotational powered, might be very similar physics somehow, and things that we think are mainly magnetic energy. Again, mainly means that what we detect when we observe them, it's mainly emitting via this way, this energetic. It doesn't mean that it doesn't have rotational power or other kind of emission. Now, it's clear that these sources are related. They cannot have different formation scenarios simply because otherwise we would run out completely of supernova core collapse explosion. Even if you consider accretion-induced collapse or other kind of formation, no way we can explain them as different classes. They should be evolutionarily connected somehow. Now, in the past years, we studied, and many groups studied how they can be connected, and actually the magnetic field formation and evolution of the magnetic fields is how connects all these sources. And I think we more or less understand the physics and the details of it. One thing that I would like to point out at this stage is how does magnetic fields in general forms in neutron stars. So there are a lot of work going on in the past 5 years on trying to simulate the field formation in proto-neutron stars. Now, one thing, there are huge difficulties, technical difficulties in doing this kind of simulation, but one thing that everybody agrees, all the simulation, and it's clear that the magnetic field can be extremely high locally. It's very easy with convective shell to create magnetic field via instabilities 10 to the 15 or 10 to the 16 Gauss locally, and it's extremely has somehow a configuration which is extremely unstable with patches, with twisted. I mean, the typical dipolar emission that we see thinking about pulsars has nothing to do with what is happening close to the crust. This can be very far away, yes, because it's what dominates, but close to the crust has nothing to do with what actually the magnetic field looks like. And this in every pulsar, in everything that has been formed via a supernova explosion of this kind. Now, how then this evolved? What happened when then you form your neutron star and is evolved? How at a certain point it comes out to be a magnetar, a radio pulsar, an X-DIN, or a CCO, or something of this kind. So here, just an idea, just one of those simulations that a postdoc of mine, Daniele Vigano, is doing. He should take the credits for this. So those are somehow luminosity, thermal luminosity in the X-rays versus time, PV dot diagram, and this is how the evolution of a 10 to the 15 Gauss magnetars from birth till several hundred mega years would look like. And here you have temperature, the field evolution, how it moves, and then depending, of course, on how you start with, so which field you get on the crust and which field is in the polar field, and then you evolve the source, you can somehow find a normal pulsar. I will show you a few more with different fields. This is low field, and this is increasing. You find normal pulsars that decays very slow, so they don't never get in this part. Luminosities are very low, or you find a very strong magnetars where you have field decay that bends. This is also the reason for which we don't see a 100-second pulsar isolated, because the magnetic field bends. For a normal pulsar to reach here will take a giga-year. For a very high magnetar to reach here, it takes a mega-year, but still the magnetic field bends. This means the field decay bends. This means that it will not slow down that much. Now, in the radio, you might have a selection effect for 100-second pulsars. You don't have such in X-rays. We see X-ray binaries at 1,000 seconds, so there is no selection effect in the X-ray band to find sources here, for example, very long period. Okay, one thing that might be somehow relevant for fast radio burst is this magnetic field that evolved in the crust. It cracks the crust, cracks or elastically moves, to say it properly, but let's say, and we can somehow have an idea on how many cracks in time, in year, depending on the field, depending on the evolution, on the age of the source is expected to do. And this is exactly the number of outbursts per year. This is a work that started Rosalba and Jose. They did some simulations. This is energetic of the bursts. This is how many per year you expect for young sources in black, and then for old, middle age and old. And those are a similar thing, but depending on the initial field you put, depending on how much in toroidal, how much in polar, there are some variables. So somehow a takeaway point in here is that it's very easy, especially for a magnet that are very young, 100 years, 200 years, to have a lot of giant flares. That's energetically not really a problem at all. The magnetic field it has is extremely strong. And at this age, depending on how you form, you can have parts with the magnetic field extremely tangled. So there is absolutely no problem in actually repeating fast radio burst if the source is, for example, a giant flare. Now, some caution, it's important here. I mean, all those simulations do not have enough physics in it to somehow simulate what happened in the very beginning of the formation of the sources. So in the first, let's say, 100, 200 years, it's more on a long-term thing that things can somehow be right. But let's say there's nothing at the beginning that can exclude or make things different from we cannot give a number, how many bursts a certain source can do per second, but certainly at that ages can be many. Energetically, they can do it. Okay, now, a connection with fast radio burst. Of course, the two main things that somehow can be related, I would say, is first the bursting activity. We know magnetars, they show three kinds. There is probably a continuum between these and these, but we like to somehow catalog them in three kinds. Short bursts, the last milliseconds, energetic 10 to the 38, 10 to the 41. Intermediate bursts, they are a bit longer, 41, 43, more or less. And giant flares. Those are more rare, of course, where the luminosities can get till 10 to the 46 in the peak. The peak here actually would go outside the building. It's just saturated any gamma ray and X-ray detector on that we know of. Okay, so those events are very common, especially in young sources. So those might be, in principle, the power of what then will become radio emission of FRB afterwards. They are also connected with outbursts, so the source does a big increase in emission because you stress somehow a part of the crust, you stress it either from outside with the bundle, from inside. There are several kind of triggers that can be possible, but then what happened in this part, there is a lot of energy dumped in there, deep also in the crust. It reacts, it gets very, very bright, and then started to cool down, and we see actually the cooling. We can measure the temperature cooling down, and the magnetosphere untwisting just during the outburst. And some of those sources actually can do several of them. And short bursts often are correlated in time where you have also a big outburst, because you have the stress, then you stress somehow the magnetosphere, and you can form the short burst too. Second thing, radio emission, of course. During these outbursts, some of those sources do show radio emission. So this radio emission, although being very similar to radio pulsars in some extent, they have also some peculiarities. So they have different spectra. They are very variable. Those are single pulses, very variable in pulse profile and in luminosity of the single pulses, extremely bright compared to normal radio pulsars. And actually, those are the polarization. They are usually linearly polarized. You see somehow, for example, jump in the PA. So they are usually linearly polarized, but not all of them. There are some spikes, some single bursts where you see only circular polarization and no linear polarization, although most of them are linearly polarized. So this is somehow to say that there are exceptions of like in FRB actually. Okay, this is somehow a game that I played when I was asked to do this talk. So just to see whether the dispersion measure that we measure in our magnetar, in our galaxy, is consistent for the one comparing to the distance they are within the galaxy. Now, in many of them, I mean, some of them, at least the radio one, have a supernova associated, so we can take this somehow as an indication of the distance of it. So this is the distance you get from the supernovae or the galactic center. This is the galactic center magnetar. And this is the distance that actually you would estimate translating their DM, usually using the DM model of the galaxy, where translating this. So you see that except for one source, actually, most of them actually are overestimating the distance of a factor of 2. It's also true, has to be said, that if you take the Yao model, that's get a bit better. They get a bit closer, probably because they're in the plane. Anyway, so although this is small statistics, so we cannot really say that the environment within those magnetars are more dense than what you would expect for the galaxy. No, I wouldn't say this, but this is somehow something that should be checked for future radiomagnetars too, for example, or try to do this better. Okay. Another things are rotation measure, polarization. I said a bit. I mean, this is DM versus rotation measure. This is in green, you have the FRBs. In red, you have the magnetars. And you see that also for magnetar rotational measure, in some cases, like the center of our galaxy, you have very big one. In some others, you have very small one. So it's very difficult to give, as in FRB, really a role to take this and interpret this. Similar polarization, probably no, you cannot see, but there are some interpulse, for example, that are purely circularly polarized, although most of the single pulses are linearly polarized in magnetars. Shape of single pulses in radiomagnetars are completely crazy. They do whatever you want. You can find 3 peaks, 2 peaks, single peaks, a big one, a small one, in the same source at 2 hours. Different observation during 2 hours. In these 2 hours, just the pulse profile changes whatever you want. Now, I don't think that there is any published detection of a sat trombone for a single pulse of a magnetar, but I think this should be searched deeper. I don't know if each of the single pulses of a magnetar have been searched for this, but certainly it's not a typical thing. Yes?
Okay. Except for the sat trombone, are also always broadband? Do you know about that? If sometimes they don't provide
Always no, but often. I mean, you can find whatever. There are some that are very small band, but just it's an exception. Sometimes, yes. Also depends on the source. Yes. Okay. And radio. Here. Yeah. Mainly, yes.
Like we've been observing with the Parkes ultra-wideband receiver, we've seen pulses all the way from 700 megahertz to 4 gigs. Yeah, they're very flat spectrum.
And very flat compared to normal pulsars, yes. Okay. Magnetars versus repeating. Of course, this is, again, very small statistics to compare. In this case, I compare only with this. I just learned about all the different, for example, hosting galaxies that are actually different depending on the fast radio burst, so it's difficult to give a direct connection. But let's say most of the things that we see in an FRB, at least in this one, in the repeating one, would fit as long as there is a reasonable way to form the radio emission, which has been many proposals that I've seen, at least this morning. So in principle, there's nothing that I would say, no way. If there is a way to create the radio emission of this kind, yes, the rest somehow fits the picture. Periodicity, this is very interesting result, of course. 16 days, it's very long. I would have hoped for 3 milliseconds, but 16 days, it's extremely long. What it is in comparison with magnetars, I cannot say. There is, at least for the typical magnetars that we observe, none of them are in binary systems. The only binary systems that are somehow reasonably, people think that they host the magnetars are the pulsating ULXs, which are these very bright binaries that we observe. They are so bright, emitting at super 18 and 10 to the 40, 41 in a close by galaxies. They show pulsations at 1 second, so they are accreting. You need a magnetar to accrete at 10 to the 41 because you have to somehow overcome the editor limit. And if you see the orbital period of those are of the order of days. Now, massive stars we know in our galaxy are usually in binaries, at least 80% of them, most of them. So there is no reason for which not to have magnetar in binaries. Probably there are less because you have kick from the supernova, but there should be, those can be one, the ULXs. And maybe this can be somehow one of the few FRB being in a binary. Not all of them should be in a binary, hopefully, we don't know, but it can be. Precession, it's also a possibility. It's also true that we don't see this precession in any of the magnetars in our galaxies. So unless there is something different, but which might be, somehow this is an open issue. Okay, bursts. Distribution of timescales of short X-ray bursts. In general, FRBs are slightly shorter, although in this distribution, there is, at least from the X-ray point of view, there might be selection effects because depend on where you decide that you define the width. This depends also on energy. So somehow they are similar. They peak at, let's say, 10 or 100 milliseconds, but I would say they're compatible. Okay. Now, radio emission during X-ray bursts that we see in magnetars. Now, this is a very difficult observationally to get this limit and to say something that makes somehow sense. We have very few simultaneous observation in radio and X-rays, where we got a burst and we were observing in radio exactly at that moment. Those few, I can maybe summarize that this is one, which is 1547, a very bright radiomagnetar. Those are X-ray bursts, and this is the peak of the radio pulse. They are more or less in phase. Another case, which actually the radio emission disappears during the bursts. So this is the galactic center magnetars. This is also very interesting. This is X-rays, and this is the phase in radio. So where you see that during the X-ray burst, the radio emission gets quenched. Third thing is actually a limit, possible limit, on the radio emission of the giant flare of 1806, found very nicely in some side band in parks. So given this, I'm not sure I'm comfortable to say whether the X-ray burst or radio burst, whether we see radio counterparts to X-ray burst. I don't know. I think this would need way more observation simultaneously. Yes?
I think I didn't understand. You think that width distribution of FRBs and of magnetar bursts is compatible? To me, they look, the FRBs...
This is a bit, they are a bit wider, yes, but it's a different band. In the sense, for example, if you see this only in very hard gamma rays, they are shorter. If you go in hard X-rays, soft X-rays, they are longer. I don't know. But yes, in general, they are maybe a bit longer, the magnetar bursts. Okay. So to somehow wrap up, some things that how can we test that there are magnetars in fast radio bursts? That's complicated without an X-ray counterpart, of course. This is the best thing that we know about the magnetars in our galaxy. So the only thing that actually is not anything new, I would say that I can say it's fast follow-up, which GCN-like triggers, like people doing in GRBs or in gravitational waves, such that this can be followed up in the X-ray band or hard X-ray band very fast. Deep searches of persistent sources, at least for the very close by image, because given the models that we have, if we have a luminosity of a source, we can have an idea on the age and on the kind of an estimate of the magnetic field the source it has at that age. Of course, you need very close by things. Giant flares in general, we can detect in all sky monitors at distance of the Virgo cluster, not farther away. So it should be very close. And of course, search for periodicities. That's of course very important. Of a few milliseconds or seconds would be better than 16 days, but that's it. Thank you.